If we look closely at the process, we can see the crude oil is first heated in a tank outside of the column. This causes it to vaporize. It then enters the fractional distillation column. The fractional distillation column will contain trays set at varying heights. Since heat rises, the hot vapor will rise in the column. The trays are set at varying heights in the column and have holes with condensing caps. These caps allow the vapor to make contact with the trays for a prolonged period as the vapor passes up through the orifice in the plate, collides with the cap, passes along the cap, and continues rising in the column. This cools the vapor, allowing some fractions to condense. The trays are set at heights that correspond to specific temperatures in the column. Obviously, the lower in the column a plate is set, the higher the temperature the plate corresponds to, since the vapor cools as it rises in the column. Therefore, the lower trays in the column will condense fractions that condense at high temperatures, and the tray set higher in the column will condense the fractions that condense at lower temperatures. The longer fractions condense at higher temperatures, and so the column collects fractions as illustrated, with the heavier fractions lower down and the lighter fractions higher in the column. So, starting from the bottom up in an atmospheric fractional distillation column, typically vaporized crude oil condenses as follows: long residual fractions, light gas oil, kerosene, naphthas, gasoline, gas. The condensed fractions collect in the trays and can be passed on to condensers, which cool them further. They are then piped to storage tanks, or they can be transported to another area in the refinery for further chemical processing. Cushioning is achieved through the design of the piston. As can be seen, inside the cylinder there is a main piston to achieve the movement of the piston rod, and attached to either end of this piston is a smaller cushioning piston. The cushioning pistons have seals attached. Alternatively, the seals may be attached to the inside of the body of the cylinder. As we can see in our example, the seals are attached to the cushioning pistons here on the piston end and here on the rod end of the cylinder. As the piston is retracting into the minus position, air is entering the rod end of the cylinder. Simultaneously, using a directional control valve, the air is evacuating from the piston end of the cylinder, shown here. As the rod retracts, the cushioning piston reaches this position, trapping some air in the cylinder. The only way for this trapped air to escape from the cylinder is through a small vent in the body of the cylinder, illustrated here. This vent has a tapered adjustment plug, which permits the size of the vent aperture to be adjusted. With the vent completely closed, the end movement of the piston rod is cushioned by the trapped air. If full cushioning is not required, variable cushioning can be applied by controlling the rate of exhaust of the trapped air. This is achieved by adjusting the size of the vent aperture as shown. Valves. Flow control valves. Now we are going to talk about flow control. The rate of airflow is what determines the speed at which a cylinder rod will extend or retract, or the speed at which a motor will run. If there is fast airflow into the cylinder will move quickly. If the airflow is restricted, the cylinder will move slowly. Similarly, the motor will rotate slowly or quickly. First, the air line is illustrated using the thick black line. A restriction in the air line is represented by two opposing segments of a circle outside the air line, as shown. If that restriction is variable, that is, the rate of flow can be altered by increasing or decreasing the size of the restriction, it is represented by an arrow through the symbol. As it is illustrated, the flow control valve will control the flow going in either direction. Crude oil is first heated in a tank, A, outside of the column, B, inside the column, C, on top of the column. The lower in the column the plate is set, A, the lower the temperature it corresponds to, B, the higher the temperature it corresponds to. What do the condensing caps in the trays do? A, they allow the vapor to pass through the trays quickly. B, they allow the vapor to make contact with the trays for a prolonged period. The trays set higher in the column will condense the fractions A, that condense at lower temperatures, B, that condense at higher temperatures. Well done! You have successfully completed the evaluation. You scored 9 out of 10. Press the Objective button to view the objectives for this level. Your objective is to connect the circuit to create the following motion displacement: A plus, A minus. This cycle must be repeated 4 times. Good luck! This level will show you how to build and test a simple pneumatic circuit. First, you will connect the air lines for the circuit. Click on the output of the compressor and drag the line to port 1 of the valve. Now, connect port 2 of the valve to the left input of the cylinder. Now connect port 4 of the valve to the right input of the cylinder. Now we need to set up the actuators for the valve. In this instance, we are dealing with roller actuators. First, connect roller 1 of the cylinder to the left pilot line input of the valve. Finally, connect roller 2 of the cylinder to the right pilot line input of the valve. Now, press the Run button to view the circuit's operation. The circuit is now running. To view the motion displacement diagram for the cylinder, click the Monitor button. Here we can see the current motion displacement of the cylinder. The next sequence to be achieved is shown to the left. The circuit will continue to operate until all the sequences have been achieved.